Right, looking at nervous and energy systems then. So with this section, what we're going to look at first of all, so we're going to look at the nervous system first, and then afterwards we will look at the energy systems and link the two together. So what we're going to look at with this section is describing the nervous system and its relation to exercise. We'll explain the role and functions of the nervous system. We'll look at the all or none law when it comes to motor unit recruitment, and then describe how exercise can enhance neuromuscular connections and improve motor fitness. Okay. Can anybody tell me? Find it. Okay. Can anybody tell me what the function of the nervous system is? What does it do for us?
Allows us to feel things.
Yeah, definitely. That's one of the things.
Allows us to move.
Yeah. So to put all of that into one kind of sentence, it basically controls all the actions of all bodily systems. So it controls everything that goes on within the body. So whether it comes to movement, whether it comes to fighting illness, digesting food, producing energy, standing upright, thinking about hormonal status, thinking about brain function, everything is controlled by the nervous system. So what it is doing all of the time is looking to maintain homeostasis. So that's the main aim of the nervous system, is to maintain homeostasis, which is basically the body maintaining balance to operate effectively. So we're looking for that normal operating procedure, everything ticking over as normal, without undue stress, without illness, without injury, and without anything stopping us from working to our full potential. Okay. So the nervous system works in different ways, but overall, what it's doing is it's taking information in, it's analyzing that information, and then creating a reaction or an action to work with that information that it's gathered. So first of all, we've got the sensory input, where we're sensing changes inside and outside of the body. So if we think about some changes outside the body, can anybody give me any examples of what some changes outside the body might be that we would need to kind of assess?
They're like hot and cold, like temperature.
Yeah, so external temperature. So if it's a hot day, then the body will sense that and react to it. If it's a cold day, the body will also react to that as well. Anything else? Think about if you're playing sport or doing a certain activity, changes outside the body.
Oh, can your heart rate increases?
So your heart rate will increase, but that's more of an internal thing that will happen. But what can happen outside the body to cause your heart rate to go up?
Wouldn't be something to do with sweating, would it? Or is that also internal?
So that's more of a temperature, and that's more of a reaction or an action that would. So if you're in a hot environment, so the change outside would be a hot environment, and then the action off the back of that would be for you to sweat to bring your body temperature down because of the external change. So what I'm thinking along the lines of is, if you're playing a sport, for example, if somebody passes you a ball in whatever sport you're playing, that's a change outside the body and you need to react to it. So whether that's getting out of the way of it, or whether that's controlling that ball, catching that ball, and doing something with it. Okay, so changes outside the body are kind of what goes on. So we're sensing those changes outside of the body. What about changes inside the body?
Something like digestion.
Yes. Can you give me an example of what change would happen if we digest something?
It could be in the digestive tract, breaking down food for the nutrients.
Okay. Go a little bit further than that. So what types of food maybe have we broken down that would change what happens internally?
Be a
So-
source of energy.
Yes, good. So, for example, if you talk about sources of energy, have you eaten something that's sugary, as in simple carbohydrate, or have you eaten something that's starchy, maybe a complex carbohydrate? So if you're eating something that's sugary, then your blood sugar level is going to go up and you'll get an energy spike. So that would be an internal change. If you've eaten something that's starchy, which is more of a slow release energy source, that energy then will be stored or released slowly for later use. Okay. Also think about if you eat something sugary or drink a sugary drink and your blood sugar level goes up, we need to react to that because the blood sugar level might go up too high for what the body is capable of regulating and capable of using. Okay, so what happens first of all then is our sensory input. So it's going to sense those changes both inside and outside of the body. The next stage is where it will interpret that information. So it will analyze and interpret the incoming information. So if we think about going back to that first example that you gave, Sinead, where we've got a hot environment. So the body will sense that change, as in it's a hot environment. The nervous system will send a message up to the central nervous system. Sorry, the peripheral nervous system will send a message up to the central nervous system saying that our body temperature is going up too high. So it's analyzing and interpreting that information. Similarly, if we're playing a sport and somebody passes us a ball, we will analyze that information. If that ball is coming really fast at us, we will basically say, okay, if that hits me in the face, it's going to hurt. And then we're trying to decide what our motor output will be, what our action will be. So when we look at body temperature, so our motor output would be to open up the sweat glands and sweat to bring the body temperature down. If it's a ball coming towards us, our motor output would be to move in a certain way to either get out of the way of the ball or to catch the ball or to control it, for example, in football, or head the ball, strike it, whatever it is. Okay, so our motor output is to respond to the information by activating the relevant bodily system. So going back to that internal example of if we've eaten something sugary, so we've eaten a slice of cake, our blood sugar level goes up. So the interpretation is that our blood sugar level has gone up too high. Our motor output would be then to send a message to the pancreas to release insulin into the bloodstream to bring that blood sugar level back down to a normal level. Is that making sense?
Yeah.
So all of the time, our nervous system is sensing the changes both internally and externally. It's analyzing and interpreting that information and then responding to that information to maintain homeostasis, normal operating procedure. So if you're ill, so say you get a cold, then the sensory input is that our systems are down, we've got a cold, we've got some sort of infection or virus. It interprets that information, then will send white blood cells, for example, different proteins to that infection to fight that infection and bring us back to our normal operating procedures without the cold or illness. Okay, so there's different ways it happens, but it is happening constantly. Even when we're sleeping, the body is analyzing what information, how much recovery do we need? So it might send us into a deep sleep. It might send protein to the muscles of the body that need growth and repair if we've done a training session that day, etc., etc. Okay, so it's constantly happening, that input, interpretation, and output. So the nervous system is split into different divisions. So we've got our central nervous system and our peripheral nervous system. Can anybody tell me what makes up the central nervous system?
Yeah, just for now.
Hi, Owen. Sorry, I missed a few minutes. Back in now.
That's right, no worries. So the central nervous system, can anybody tell me what makes up the central nervous system? This is head office, if you like. The main control room.
Is it the brain?
Yes, the brain and the spinal cord. Okay, so the brain and the spinal cord make up the central nervous system. So that is where all the information is sent. That is where it's all analyzed, and that is where the action is sent from. Okay. We've then got the peripheral nervous system. Let me just show you this. So, don't know if you can see the skeleton here. Oh, hold on a second. Let me just change my background if I can. And change my background. Okay, there we go. Sorry about that. Okay, so what we've got here is we've got the spinal cord. Now, as it runs down the middle, I don't know if you can see the yellow bit that comes down along the middle of the spinal cord. So that is part of the central nervous system. What we've also got are these sections that come off of the spinal cord. So this is the start of our peripheral nervous system. So our peripheral nervous system branches out from the central nervous system, the spinal cord, all the way around the body. So the spinal cord runs right down the center of the vertebrae, and then our peripheral nervous system are these yellow sections that are sticking out here that will then spread out all the way around the body, our peripheral nervous system. So messages are being sent from peripheral nervous system to central nervous system, the brain and spinal cord, and then back out to the peripheral nervous system with the action that needs to occur. Okay. So the peripheral nervous system branches into two sections. Does anybody know what they are? I've sent you these slides, so I might be giving you the answers. The peripheral nervous system splits into the somatic and autonomic sides. So our somatic side is our voluntary side. We control it. We decide what actions are to take place with this side. Our autonomic side is our involuntary side. We don't have any control over what happens on this side. So if we think about our earlier session when we spoke about voluntary muscle and involuntary muscle, so the somatic side controls voluntary muscle. We decide to contract, we decide to relax those muscles. The autonomic side is our involuntary muscle, like the digestive tract, the artery walls. We don't control the contraction or relaxation of those. Okay, now our autonomic side also branches into two sections. Does anybody know what they are? Okay, so the autonomic side branches into our sympathetic and parasympathetic. So the sympathetic, as it says in here, is our war, high stress situations. A parasympathetic is peace or low stress situations. So let me give you an example as to how all of this works. So let's think about exercise first of all. So we decide to go for a run. Okay, so the somatic side, skeletal muscles. So we are running. We can decide to keep running. We can decide to stop if we want to. So we're going to run. Now, what do we think happens internally as we go for our run? So what happens to heart rate? What happens to breathing rate? What happens to body temperature, etc.?
All increases, yeah?
It all increases, yes. So that is the sympathetic side of our autonomic system. So internally, so we've got no control over it. We're influencing it by running. But then for us to keep running, our nervous system interprets that information. So if I want to keep running, I need my heart rate to be up. I need my stroke volume to be up. I need my cardiac output to be up. I need everything to be up for me to keep going with my run. So the autonomic side kicks in to increase heart rate, to increase stroke volume, etc., for you to keep running. When we stop running, what happens?
Sorry, I want to say that again.
When we stop running, what happens?
Everything low.
Oh, yeah, everything reduces, your heart rate lowers, blood pressure comes down.
Yeah, everything comes back down again. So that is the parasympathetic side of the nervous system. Okay, so the parasympathetic side of the nervous system is when everything is coming back down the other side. Sinead, are you okay? I saw you got kicked out there for a second.
Yeah, it's fine. Sorry.
Cool, no worries. Did you catch what it was talking about? I'll recap it anyway. I'll recap it. I'll recap it.
yeah.
I'll recap it. Okay. So we've just been saying that when we stop running and we do our cool down section, the parasympathetic side kicks in. And as Adrian said, everything comes down. So heart rate comes down, breathing rate comes down, body temperature comes back down again. So the parasympathetic side kicks in. So we decide to go for a run. So as we're running, we need to fuel those muscles. We need oxygen to those muscles. We will find that our body temperature will go up because of the contraction, relaxation of the muscles. So the sympathetic side will kick in to bring everything up. And to help us maintain that running or that exercise intensity, the sympathetic side will kick in. When we stop or when we slow down, the parasympathetic side will kick in to bring everything back down again. Breathing rate back down, heart rate back down, body temperature back down again. So as we are doing our exercise, the sympathetic and parasympathetic system are constantly analyzing and deciding, right, we need to up things or no, we need to down things. So the parasympathetic side might go, okay, we've slowed down a bit. I can bring my heart rate down a bit. Okay, my intensity level's gone up again. So the sympathetic side will kick in. So if we think about interval training, so let's say you're doing a minute on of really high intensity, a minute off of really low intensity or even rest. So during our minute on, sympathetic side kicks in. During our minute off, we swap it over. Parasympathetic side will kick in, recover, recover, recover. Then we'll kick it in again and it'll keep swapping over. To eventually, when we stop our exercise after our cool down and we're recovering later on and we come to full recovery, everything balances off again. Okay, homeostasis. Does that make sense?
Yeah.
Yep, got it.
Cool. So that's an example of exercise, but we can also think about more internal stuff. So let's go back to our example of we've eaten a nice big slice of cake. So what happens here is as we've eaten our slice of cake, we're releasing all that sugar, all of the badness, if you like, into the system. Okay, so the sympathetic side kicks in. So our blood sugar level goes up, our energy level goes up because of our sugar spike. Now, because it's gone up and we're not really using it, we're not doing exercise, we're just sitting on the sofa watching something on the telly, and our blood sugar level has gone up and we're not burning it off, we're not using it, the parasympathetic side then will kick in and say, right, it's up too high and we're not doing anything about it. So it'll release insulin into the system to bring that sugar level back down and bring us back to homeostasis. Okay. We think about body temperature. We go for a nice summer's walk during the day, but it's 24, 25 degrees. Body temperature goes up. Sympathetic side, we start to sweat. Parasympathetic side kicks in to bring us back down to homeostasis, our normal body temperature. Okay, so sympathetic and parasympathetic are always doing this to try to maintain that balance of homeostasis. We can influence what happens with the sympathetic and parasympathetic side by eating certain foods, by putting ourselves in certain situations, by doing exercise and activity, by playing sports, by playing a computer game, for example. So if you think about playing a computer game, the mental kind of ability, you need energy, concentration levels. So the sympathetic, parasympathetic side are again fueling that and giving you the brain function to be able to continue with the game or whatever it is that you're doing. Okay, so it's constantly working. Okay, so depending on the training that you do, again, will affect how the sympathetic and parasympathetic side react to the type of exercise or training that you're doing as well. Okay, so question for you. Have a think about this one. Adrian and George, you might have heard this question before, so hang fire a sec if you have. Okay, so we've got a hot plate. Okay, so you're doing some cooking on a hot plate. You put your hand on the hot plate. Okay, is that when you take your hand off the hot plate, is that the somatic side or the autonomic side kicking in to take your hand off the hot plate?
Was that the somatic because you're deciding to lift your arm up?
Yeah, exactly. So even though it seems like an automatic reaction to take your hand off, you can decide to put your hand back on there if you really want to. Okay, so because it's hot, because it's causing damage, the speed of the message that is sent kind of seems like it's an automatic reaction. You didn't really think about it. You just kind of did it. But it is a somatic, voluntary movement or action. Okay, does that make sense? So as I said, you could put your hand back on there if you really want to do, if you can take the pain. But it is causing damage. So because it's causing damage, the sympathetic side basically sends a message going, take your hand off of that plate because you're going to cause damage to your fingers or whatever it is. Okay, happy with that? Any questions before I move on? Okay, so our responses to training then. So when we do exercise, the nervous system will have different responses. So the main response is that it will strengthen and grow new connections within the nervous system, speeding up the frequency of nerve impulses to the motor units. Now, what that means is strengthening and growing new connections. Basically, we're learning new things, and it will also speed up the nerve impulses. So what that means is it's the messages being sent from peripheral to central back to peripheral again are a lot quicker. So if you think about reaction times, so you're playing a sport, by training, zigzag running or reactions. So when it comes to like 100-meter sprint, that gun going off for you to start the race, the gun going off, you reacting. So the more you do it, the more you repeat it, it will speed up the nerve impulses, the message being sent back and forward, and impulses to the motor units. So I'm going to talk about motor units in a second. It'll also improve the synchronous recruitment of motor units, resulting in stronger muscle contractions. And what that means is that we're going to recruit more muscle fibers to then be able to lift heavier weights. So you get a stronger muscle contraction. And linking to that is we've got muscle fiber recruitment. So the nervous system controls muscular contraction. Motor units consist of a single motor nerve and all the muscle fibers it innervates. Know that. Seen that question come up on the paper quite a bit. So motor units consist of a single motor nerve, so a single nerve, and all the muscle fibers that it connects to, that it innervates. When the message is sent from the central nervous system to the muscle, all of the fibers in that motor will be recruited when the stimulus is sent from the nervous system. So it's the all or none law. So if the central nervous system sends a message out to the peripheral nervous system, to the muscle fibers that connect to that motor unit and tells them to contract, they will contract 100%. If the nervous system tells those muscle fibers not to contract, they won't do anything at all. So those muscle fibers will either contract 100% or not at all. If we need more strength, more units will be recruited. So if the weight gets heavier or we increase the weight, the nervous system will assess the situation and say, right, we need to recruit more muscle fibers, more motor units to lift a heavier weight. Okay, and I'll give you some examples of that. So what we've got here is central nervous system, a spinal cord. Branching out from that, we've got our peripheral nervous system, and it's bringing us all out to our skeletal muscle here. What we've got then is motor unit number 1 is connected to this muscle fiber and this muscle fiber. Motor unit number 2 is connected to this muscle fiber, and this muscle fiber. So if I've got, I want to pick up my phone. So the sensory input is that I decide I want to pick my phone up. The central nervous system will analyze that information and interpret it and basically say, we don't need much strength to lift up the phone. So it will send a message out to motor unit number 1 and say that this muscle fiber and this muscle fiber are going to do this job and this work of picking up the phone. Okay. If I then decide I want to pick up something heavier, so let's say I'm going to pick up the skeleton, okay, which is heavier. It would then say, okay, we need more strength because it is, so the analysis has basically said that it is heavier than the phone. we need more strength to pick up the skeleton. So now we're going to use motor unit number 1, and we're going to use motor unit number 2. So these muscle fibers will contract fully 100% to pick up the heavier weight. So the more heavier the weight, the more motor units and more muscle fibers are recruited. If we go back to something lighter, then it'll reduce the amount of motor units and muscle fibers that are recruited to lift. So putting that into exercise then. So if we're doing strength training and we want to get stronger, what's actually happening is our nervous system adaptation. So say, for example, today we lift 100 kilograms on a deadlift, and we've used 80% of our muscle fibers to do that. During our recovery phase, our central nervous system will basically say, if we want to do that again, we're going to need bigger and stronger muscle fibers. So those muscle fibers, during strength training, we will create micro tears in the muscle fibers. So those muscle fibers will repair bigger and stronger for us to lift that weight again, or to lift a heavier weight again. So when we do strength training, the training session itself, yes, it's important, but the recovery phase is probably more important because that's where the adaptation occurs. That's where the muscle fibers will repair and grow bigger and stronger. Are you with me? Yes, no?
Yeah, kind of.
Sure. Do you want me to recap it
Yeah.
again? I can recap it again.
If you could.
I'll give you some other examples. So I've used this one on the course with Adrian and George before as well, but it could help. So let's say you are working in the gym and a new 50 kilogram dumbbell has been delivered to the gym. You've been asked to move the dumbbell to the gym floor. So when you go up, let's say the dumbbell is in a box, okay? So you can't see the actual dumbbell, but it's just a box with the dumbbell inside. When you go to pick up the box, what's actually happened is somebody's taken the dumbbell out of the box already and resealed the box. So in your head, the central nervous system has said that that's a 50 kilogram weight. That box is going to weigh 50 kilograms. So you will recruit lots and lots of muscle fibers to lift 50 kilogram box. However, because the box is empty, what happens when you lift the box?
It's just going to fly up, isn't it?
Yes. And the reason being?
Because it weighs less than what you think it is.
Yeah. And you've recruited too many motor units and too many muscle fibers for the actual job in hand. So if you've recruited enough muscle fibers to lift 50 kilograms, whereas really you only need to lift 3 or 4 kilograms of a box. Okay, probably not even that. So let's flip it the other way. So you think the box is empty, however, there's a 50 kilogram dumbbell inside it. So what happens now when you go to pick it up?
It's not going to
Get
go
that back.
Yeah, you probably wreck your back, number one, but number two, it's not going to go anywhere because you haven't recruited enough muscle fibers for the job at hand. You've only recruited enough muscle fibers to lift an empty box. What then happens is, because the speed of the messages is so quick, the nervous system will basically go, right, recruit, more, and then you probably will pick it up, but with really bad technique, and probably cause yourself an injury and drag it up along your legs. Whereas if you take a step back, the nervous system will go, hold on a second, there's 50 kilograms in there, I need to recruit more. So you recruit more, and then go and lift the box up with good technique. Is that making sense?
Yeah, I understand that. Thank you.
Sure. Cool. Okay. So moving on to the next section, then we're thinking about special populations and the nervous system. So there are many disabling neurological diseases and disorders that can affect the nervous system. Okay, so we need to think about it again on a case-by-case basis with this. With the aging population, there's potentially a slower processing time. So if we ask somebody who's of an older age, who maybe is not used to exercise, to do a certain exercise, to you it might be quite simple, but for them it might take them time to be able to kind of analyze the information, adapt it, and then perform it with good technique. Okay, so a slower processing time. There's potentially an increased risk of falls as well, because reaction times can increase. So if something if they start to fall, if they trip, for example, they can't really correct themselves as much as they used to. Okay, again, we take this on a case-by-case basis, but it's just something to keep in mind, that if we ask them to ask somebody to do a complicated exercise with complicated movements, to make sure that we look at working technique first, practice technique until we've got the technique right, and then start to challenge a little bit more by adding weight or different increments to challenge. Okay, and that is our nervous system. Any questions before we move into energy systems? Okay, so straight into energy systems then. What we're going to look at here is describing how carbohydrates, fats, and proteins are used in the production of energy. We'll explain the use of the 3 energy systems during aerobic and anaerobic respiration, and then we look at the effects of age, pregnancy, and disability on the energy systems. First of all, where do we get our energy from?
From what we eat, drink.
Exactly. So energy comes from the food we eat. What are our 3 main energy sources when it comes to food? When we break
fats
down,
and protein.
good. Carbohydrates, stored in muscle and liver cells in the form of glycogen. Fats, stored as adipose tissue. And proteins, their main function is the building material for growth and repair, but they will become a source of energy when your carbohydrate and fat stores have depleted. Okay? So your 3 sources of energy are carbohydrates, fats, and proteins. Carbohydrates and fats first, and then when they run out, we'll kick into protein as an energy source. So it looks a little bit like this when we break it down. So on the left-hand column, we can see the food that we eat. Once we digest it, it's absorbed into the blood and transported around the body to the active cells for immediate use. When we digest our carbohydrates, we convert them into glucose. This is stored as glycogen and converted into ATP, which we'll look at in a second, which is your energy currency to be used immediately. Fats in the form of fatty acids, when it's broken down, it's stored as adipose tissue and again will be converted into ATP to be used as energy. Our proteins, when we break them down, they're broken down into amino acids. Their main function is growth and repair of tissues. However, because they're stored as fat, when we run out of our carbohydrates and fats, this storage of protein, we can then convert it to ATP to be used as an energy source. Okay, so hopefully this will become a little bit clearer as we move in here. So energy is released in the body by the breakdown of carbohydrates, fats, and proteins to produce adenosine triphosphate, which is the body's energy currency. Bear with me. Sorry, so I skipped ahead, but I hadn't. Okay, so ATP, adenosine triphosphate. So this is an energy-rich compound comprising 1 adenosine molecule bound with 3 phosphate molecules. Okay, so as you can see, adenosine, 3 phosphates. Energy is stored in the bonds that link the phosphate groups to the larger adenosine molecule and are called high energy bonds. So these green links here, this is where our energy is stored. ATP releases or liberates its energy when one of its 3 high energy bonds is broken. So when we break that bond, that's when energy is released. We are then left with adenosine diphosphate plus a floating phosphate molecule. How can we get back to ATP? How can we re-energize, if you like?
Creatine phosphate.
Not creatine phosphate. We're going to come on to that in a second. So if I've got lots and lots of ADP and phosphate, so I've used up lots and lots of energy, how do I get back to ATP? How do I get energy back again?
Eating.
Eat. Exactly that. Refuel. So by refueling, by getting more carbohydrates, fats, and proteins potentially into the system, we can then get lots and lots of ATP back again. So if we think about long distance runner, they can refuel as they're going through their event. So they'll use up lots and lots of ATP, and then they'll have, whether it's energy gels, whether it's energy drinks, anything like that, even food to take on board, they can then re-energize, so get lots and lots of ATP back again to carry on with their event. Okay, so we're going to look at the 3 energy systems next. Can anybody tell me what the 3 energy systems are? George, I think you said one.
Creatine phosphate.
Creatine phosphate energy system is 1.
Aerobic.
Aerobic.
Anaerobic.
Anaerobic lactate system. Good. Okay, so the first one we're going to look at is the creatine phosphate energy system. So creatine also has a high energy bond with phosphate. So as we can see here, so creatine is linked with phosphate, and we've got our high energy bond. When this bond breaks, the released phosphate molecule, the released phosphate molecule is free to attach itself to an ADP and turning it back to an ATP. So then we can use that as an energy source. So this chemical reaction happens very quickly. However, like ATP, creatine phosphate stores are very limited. So the creatine phosphate system is therefore used for activities of high intensity, low duration. So what we're looking at here, when we talk about duration, we're talking about anything up to 15, 20 seconds, something like that. Can anybody give me any examples of sports, events, activities where you are predominantly using the creatine phosphate energy system? So high intensity, low duration.
Sprints.
Sprints, yes. So 100-meter sprint is creatine phosphate energy system. Pure power, explosive, high intensity, low duration. Anything else? Think about those field events when it comes to athletics. So long jump, high jump, shot put, discus, javelin, all those type of events, explosive, high intensity, low duration. We think about team sports, we can look at a scrum in rugby, all about explosive power. We think about tackling in rugby, football, anything. So we go into a tackle quite hard with high intensity. Obviously lasts for a split second. We could put, when we talk about our sprints, we've got 100 meters. We could potentially put 200 meters in there as well, but you are kind of moving a little bit into the next energy system, but predominantly creatine phosphate system for 200 meters. Okay, so when we train the creatine phosphate system, high intensity activities have a significant training effect. They can result in increased muscle mass and a predominance of fast twitch muscle fibers. So when we train our CP system, we're predominantly training our fast twitch muscle fibers. So we're going to make those muscle fibers bigger and stronger, which means that because we've got bigger and stronger muscles, we can store more anaerobic fuel sources, such as ATP, creatine phosphate, and glycogen. So we can store more energy in those larger muscles. Our next energy system is the lactate energy system. So to explain this, glucose is a carbohydrate found in either the blood as blood sugar or in glycogen, which is a stored form of glucose. There are two ways by which glucose can supply energy, one dependent on the presence of oxygen, which is aerobic, the other not. The lactate system does not require oxygen and allows rapid ATP production to continue beyond the few seconds of the CP system. However, without oxygen, the glucose molecule cannot be broken down fully, which results in a waste product called lactic acid being produced. So the lactate system will last up to about 3 minutes. Okay, so it doesn't last very long, but it lasts beyond the time of the creatine phosphate system. Can anybody give me any examples of where we would use the lactate system?
It'd be quite fast-paced exercises.
Yeah, give me an example.
See martial art.
Interesting.
What was the question? Sorry.
Some examples of where we would predominantly use the lactate energy system. So it's still high intensity, but it lasts from 20 seconds up to about 3 minutes.
Swimming.
Okay, depends on what swimming you're doing. Give me a distance.
50 meter.
50
100
meters. 100 meters. Yes, 100 meters, 50 meters for swimming is going to predominantly use the lactate system. So you're basically going to try and get there as fast as you can, is what I mean. So 50 meters or even 100 meters will predominantly use the lactate system. So what we're thinking about here is thinking about that burning sensation in the muscles, the buildup of lactic acid. 400 meters. So if you're watching athletics, 400 meters is a perfect example of the lactate system in action. Because you start off with the CP system, so you start off as fast as you can. The CP system will only last to about 20 seconds, and then it's hang on for as long as you can, basically until you can finish. You're trying to maintain the same speed, but that buildup of lactic acid in the muscles is our lactic acid system. So when we train the lactate system, they're primarily related to the cardiorespiratory system. So even if you're doing interval training, where you're working, for example, 2 minutes on, really high intensity, 1 minute off, you'll feel your legs burning, whatever it is, muscles that you're using, you'll feel those muscles burning. However, muscles that receive and utilize more oxygen produce less lactic acid at a given exercise intensity. So when we train the lactate system, what we're actually doing is making our heart muscle bigger and stronger. And we're also increasing our lung capacity to be able to take in more oxygen, get it to those muscles so we can produce less lactic acid. So what we find by doing regular anaerobic training is we build up an ability to buffer the effects of lactic acid, but also a mental tolerance to shut out the physical pain and the physical discomfort. So the main effect then is that you can work harder for longer. So if we're working at a certain intensity today, where our body is screaming at us to stop, if we continue to train using the lactate system, 4 weeks down the line, we should be able to do the same session with less pain and with less buildup of lactic acid. And then resulting in that is that we can push ourselves that bit more. So working harder for a longer period of time. Does that make sense?
Can I ask a question? Sorry.
Sure, yes.
Because I'm a swimmer, we'll do, say, like 50 meters sprints 20 times, and then we have to do, say, 200 to 400 meters of lactic removal. So just swim like really slow compared to the sprints. How does, say if we're like sprinting, 10-second rest, sprint again, or like 5-second rest, how does then going straight from that into swimming, say 16 lengths really slow, how does that like repair and like, is it like get rid of the lactic acid, like it's lactic removal?
Yeah, so the lactic acid build up within the muscles, okay? So to remove that lactic acid, what we need to do is we need to keep the muscle moving, contracting and relaxing, so we can increase the blood flow through it. So what we're doing by doing it slowly is that we're then, by doing that slow one, we're actually moving into our next energy system that we're going to look at, our aerobic system. So using the aerobic system is we are using oxygen, but we're doing it at a slower pace for a longer period of time. So you think about 16 lengths, it's going to take you a longer period of time, and you're doing it slowly. So you're going to get more oxygen into the body, oxygen into the system, and then that oxygen is going to come in to buffer the effects of lactic acid, and it's going to help to sweep away that lactic acid. Okay.
So what would happen? Sorry.
Go on, sorry.
What would happen if you just did a load of sprints and then just stopped and didn't do lactic removal?
Yeah, so you've got that lactic. So you think about cramping, you think about the effects of DOMS, you'll stiffen up later in the evening. So it's gonna, yeah, that lactic acid build-up will affect you later.
Yeah.
Yeah. Does that make sense?
Yeah, thank you.
Cool. So if you just look at this sentence here, muscles that receive and utilize more oxygen produce less lactic acid at a given exercise intensity. So during your 16 length recovery phase, you're getting lots and lots of oxygen to those muscles to stop the lactic acid buildup. And because you've increased the blood flow, that blood flow going through the muscle is going to bring that lactic acid out and get rid of it. Okay.
Okay, thank you.
Cool, no worries. So the aerobic system then. So the aerobic energy system is dominant during lower intensity activities when ATP demands are low and oxygen is plentiful. So we've got lots of oxygen coming in. So the two macronutrients that supply the body with ATP during aerobic metabolism are fats in the form of fatty acids and carbohydrates in the form of glucose. Our waste products produced are carbon dioxide, water, and heat. So carbon dioxide, obviously, as we breathe out, we're going to produce more carbon dioxide. Sorry, as we work, we're going to produce more carbon dioxide. So our breathing rate will go up to get rid of that carbon dioxide. Water in the form of sweat, but also we lose water through our respiration. So you think about it, if you breathe on your hand, you can feel it's wet. So we use up water that way, and heat as your body temperature goes up. However, there are almost no limits to the amounts of ATP that can be produced using this energy system. So if we think about long distance runners, triathletes, etc., they can fuel as they go. So they can get more ATP on board to continue with the event or activity that they're doing. So long distance runners, so even anything from, we think, a 5K or even less than that, 1,000 meters, 1,500 meters and up. When it comes to long distance swimming, it's not a sprint race. It's more of a longer distance where it's slower, it's more controlled, breathing rate is lower, and you can even fuel as you go as well, as you go along with that as well. So when we train the aerobic system, so we're doing kind of slower paced exercises, high repetitions when it comes to weight training, our pulmonary changes. So improvements in the efficiency of the respiratory muscles. So the diaphragm and intercostal muscles become more efficient. We can then increase our maximal breathing rate and tidal volume. So that's the amount of oxygen that we pull in each breath can increase. The heart of a trained individual shows significant hypertrophy, so the heart muscle itself gets bigger and stronger. We get improvements in coronary blood flow, so the flow of blood to the heart muscle itself improves. Increased stroke volume, the amount of blood pumped per beat, and an increase in muscle capillaries. So we can increase our capillary beds within the muscles to get more oxygen to them. For muscular changes, we get increased size and number of mitochondria. So those powerhouses that are bringing our energy, our nutrients, etc., to the working muscles will increase. The trained individual is therefore able to take in, transport, and utilize more oxygen. Any questions on that?
No.
Okay. So what I've got here, now I won't go through all of this, but this kind of shows you how we can split our energy systems through different sports. So this is done in percentages. So just at the top one here, we can see basketball, 60% of it is the phosphocreatine system. 20% of it is the lactate system, and 20 of it is the aerobic system. So if you think about basketball, we have players that will come on up and down the court, for a period of time. It's like jumping, it's sprinting. So it's 60% creatine phosphate. 20% of it is lactate system. So as we move outside the PC system, it's here, but then they need to be able to last the whole game, but it's on for 5 minutes, off for a certain amount of time to recover, on for 5 minutes. So there's not as much demand on the aerobic system, because when they're on the court, it's quite high intensity. If we look at golf swing, for example, 95% creatine phosphate because of the swing. Running distance, 10% creatine phosphate, your sprint finish, 20% lactate, and 70% aerobic. Okay, so I won't go through them all, but you can kind of see how we split the energy systems and how they're used. Okay, so just to go there, Sinead, you're swimming. So 50 meters freestyle, 40% of it is creatine phosphate, 55% of it is lactate system, and then only 5% of it would be aerobic. So that's, you know, swimming as fast as you can for 50 meters.
You know,
And then-
you're talking about the creatine phosphate, the energy system.
Yeah.
What is it when people would take creatine when they go to the gym and stuff?
Okay, so your body produces natural creatine. Now, if people take on extra creatine, the reason that they would take on extra creatine is to work that system more. So you'll find that those people are using high weights, low repetitions, and doing power-based exercise. So what they're trying to do is give themselves an advantage when it comes to using this system. So what they want to do is they want to build muscle mass, and they want to build more power in their muscles. Your body has got a natural creatine production system. So if you take extra on board, it can have a detrimental effect to the system. So your heart rate will shoot up, your breathing rate will shoot up. So it can have a detrimental effect. So to be perfectly honest with you, when I've trained clients who are looking at increasing muscle mass, power, etc., don't use creatine. There's no need for it because your body produces enough. And we can also look at nutrition. So when it comes to nutrition, we can look at nutrition to help increase the creatine, the natural creatine production within the body. Does that answer your question?
Okay. Yeah, thank you.
Sure. Cool. Okay, final one then is our waste products. Okay, so I've put this slide in here because I've seen this question come up on the paper. So what waste products or what byproducts are produced by using the three energy systems? So if we use the creatine phosphate system, we've got no waste products produced at all. For the lactate system, our waste product is lactic acid, and for the aerobic system, our byproduct is carbon dioxide, heat, and water. And that concludes the energy systems. Any questions?
No, that's all good. Thank you.
No, sure. Okay. So what we'll do, let me just stop the recording.